Hi guys, it's Mr. Robeson here, back with AP Statistics. Today we're going to look at the sampling distribution of two different means. So we're going to be subtracting two means, and what is the sampling distribution of that going to look like? All right, so recall we had a few formulas long ago, back in, I guess, first semester, where if we were combining the mean of two distributions, we would just subtract those two means. If we wanted to combine the standard deviations, it was just like the Pythagorean theorem. C squared was a squared plus b squared, so we would take the square root of both. So we square both standard deviations and take the square root. And if we had three, we would just do the same thing for like a third one. It doesn't matter if we're subtracting or adding, we still add in between them. All right, so let's take a look at an example here. The heights of 10-year-old girls are normally distributed with a mean of 56.4 inches and a standard deviation of 2.7. So let's see, the mean height for the girls is 56.4, and the standard deviation for the girls, so I'm using sub G for girl, is 2.7. The heights of 10-year-old boys are normally distributed with a mean of 55.7 and a standard deviation of 3.7. So the mean for the boys is a little bit less, 55.7, and the standard deviation for the boys is a little more. So it looks like the boys' heights are a little more spread out at that point. What is the mean difference in the heights, girls minus boys, and its standard deviation? All right, so the mean difference for girls minus boys would be the mean height for girls minus the mean height for boys. So it's 56.4 minus 55.7, which I believe gives us 0.7, and this would be in inches because both of everything up here was in inches. All right, next up, the standard deviation. So the standard deviation for the difference in the heights, girls minus boys, would be the square root of standard deviation for girls, which is 2.7 squared, plus the standard deviation for boys, which is 3.8 squared. So we're just going to have to throw that into the calculator and see what we get. Let's see, where's our calculator? There it is. All right, making some lists, it looks like. Second square root, 2.7 squared plus 3.8 squared. And we get 4.66. All right, so when we do combine distributions, it tends to have a larger standard deviation if we're just combining the distributions. But we're now going to look at what happens when we have certain samples from each distribution. So now if we have a sampling distribution, well, the sampling distribution of the difference is normal if both distributions are normal. So if they tell us ahead of time everything's normal, then the sampling distribution will also be normal. All right. If our sample sizes are greater than 30, that also gives us that it's normal by the central limit theorem. All right. We could also have the last option usually is to take a look at the graph and see is there no outliers in it, not strongly skewed. And we can also mix and match. So like maybe one of the distributions is normal, but the other one, it doesn't say anything, but the sample sizes are over 30, that's fine. Or maybe one of the samples is over 30 and one of them's not, and we don't know if either one of them's normal. Then we'd have to look at the graph for one of them. So we can mix and match these things together to get that something is normal. All right, with our last example, which is here, we had normally distributed girls' heights and normally distributed boys' heights. So both of them satisfied this first condition here, so the sampling distribution would have been normal as well. All right, so the mean for the sampling distribution would still just be M1 minus M2, or the first one minus the second mean. And the standard deviation, now that we're working with a sampling distribution, we're dividing by the sample size for each one now. This is just like we did before, like we had the standard deviation divided by the square root of n was our sampling for x bar. Well, now we're doing the same thing. If we square this, we could bring it back under the square root, and then we're just adding them together. All right, so same deal happening. And it's actually, if we did the Pythagorean theorem, this is the exact same thing that would work. All right, so now we've got the same information as before. So like with the mean height for the girls was, well, we've already, there we go. The average height, okay, so we're going past that. We're just looking at the sampling distribution. Mean difference in heights and its standard deviation. So the average height for the girls, so now we're doing x for the girls bar minus X bar for the boys. So the average height for the 12 girls was 56.09, and the average one for the boys was 54.68. All right, so we could just throw that in the calculator and get that answer for the sample mean difference. 56.09 minus 54.68 gives us 1.14. Okay. 1.41, I think it was, not 1.4. Yeah. All right. Now for the standard deviation, if we want to do for the sampling distribution, so they told us these standard deviations to begin with, which is cool, but we usually don't know that information. So the standard deviation for the mean girls minus the sample mean boys is equal to the square root of, let's see, so we're doing girls first. The girls was 2.7, and we took random samples of 12 girls. So we get 2.7 squared over 12. Plus for the boys, we were taking samples of 8 boys, and their standard deviation is 3.8. So it's 3.8 squared over 8. So we're just throwing that in our calculator now. I'm going to move this over so we can see. So we get the square root of 2.7 squared divided by the 12 people in that sample plus 3.8 squared divided by the 8 people in that sample. Now, most of the time, this won't really be the case. Like, we won't have the population information. So we'd be doing standard error instead of standard deviation, but that's really what we're gonna use, and it works the exact same way. So this is 1.55, also in inches. All right, so notice this was a lot smaller than it was on the last slide. So on the last slide, it was like, what, 4 point something? And on this slide, it's 1.55. So when we have sampling distributions with those sample sizes, it makes our distribution less spread out. Our standard deviation gets smaller. All right, so another example here. If you want to try this one on your own, you can pause it. So a fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid dispensed in the machine follows a normal distribution with a mean of 27 ounces and a standard deviation of 0.8. So this was the large setting, so the mean for the large is 27, and the standard deviation for the large is 0.8, and it is normal. That's cool. All right. When the medium setting, so now we're on to medium, is chosen, the amount dispensed follows a skewed right distribution. So it's no longer normal. With a mean of 17, so the mean for medium is 17 ounces, and the standard deviation for the medium is 0.5 ounces. To test the manufacturer's claim, the manager measures the liquid in 25 cups. So the number for the large is 25, filled with the large setting, and 35 using the medium setting. So the number for the medium is 35. So this is greater than 30. So by the CLT, this would also be normal. All right, so both of them end up being normal. So we do get that the distribution would be normal. Cool. All right, mixing and matching. What is the mean and standard deviation for the distribution for the sample mean, or the sample mean for the large minus the sample mean for the medium? All right, well, the mean is probably the easier one to do. For x bar L minus x bar M, it's just the difference of these two means. So it'd be 27 minus 17, which is 10, and I believe we are working in ounces, OZ. All right, the standard deviation for x bar L minus x bar M would be equal to the square root of, let's see, where standard deviation, 0.8 squared over 25, that's sample size, 0.5 squared over 35, its sample size. And we're just throwing that into the calculator. Move my calculator out of the way again. Second square root, 0.8 squared divided by 25 plus 0.5 squared divided by 35, and enter. 0.18. All right, so it actually gets smaller, which it should because we're working with the sampling distribution and we have big samples. So I guess this would round to that one. I'm not sure why it was slightly different. Oh, that's right. I changed the numbers and I didn't update these, but okay, we'll go with that one. But this is actually what it is right there and right there. Forgot to update the answers here when I changed the numbers, but no worries. That's how we do it. All right, so that is how we work with sampling distributions. The next video will come in, and I think we'll start doing confidence intervals.